Carbon and its compounds. Carbon compounds play an important role in our day-to-day life. Things like toothpaste, soap, cosmetics, medicines, clothes, paper are carbon compounds. Even the bread we eat is a carbon compound. If we burn the bread, we get a black substance that is nothing but carbon. The amount of carbon present in Earth is very less. The Earth's crust has 0.02% of carbon in the form of carbonates, hydrogen carbonates, coal and petroleum. The atmosphere has 0.3% of carbon dioxide. We have already learnt about ionic compounds. Let us see some important differences between ionic compounds and carbon compounds. Carbon compounds are poor conductors of electricity. That means they do not conduct the electricity, whereas ionic compounds are good conductors of electricity. The boiling points and melting points of carbon compounds are less compared to ionic compounds. For example, the boiling point of acetic acid, which is a carbon compound, is about 118 degrees Celsius, whereas the boiling point of an ionic compound like sodium chloride is 1413 degrees Celsius. In carbon compounds, the force of attraction between the molecules is not very strong, whereas in the ionic compounds, the force of attraction between the molecules is very strong. The bonding in carbon compound does not give rise to any ions. The bonding in ionic compounds gives rise to ions. Bonding in carbon compounds. The atomic number of carbon is 6. The outermost shell has 4 electrons, so its valency is 4. Generally, ionic compounds attain the noble gas configuration by either losing or gaining electrons. But carbon cannot do that. Let us see why. If carbon gains 4 electrons, it would be difficult for the nucleus with 6 protons to hold on to 10 electrons. If carbon has to lose 4 electrons, it would require a large amount of energy to remove 4 electrons. Then it turns into a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. So, losing and gaining of electrons does not work with carbon to make bonds. So, carbon cannot form ionic bond. Covalent bond. Carbon make covalent bond with other carbon atoms or with atoms of other elements. Before we see the covalent bond in carbon compounds, first study the covalent bond formation in hydrogen, in oxygen and in nitrogen molecules. Covalent bond. A covalent bond is a chemical bond formed by the sharing of electrons between two nonmetal atoms. Let us see covalent bonds in hydrogen, oxygen and in nitrogen molecules. Hydrogen atom has a single electron in its K shell. It attains the nearest noble gas helium's configuration by sharing its single electron with another hydrogen atom. Two hydrogen atoms share their single electrons to form a molecule of hydrogen. Since only one electron is shared by each atom, a single covalent bond is formed between them. Oxygen has 6 electrons in its L shell. It needs 2 electrons to complete its octet. So each atom of oxygen contributes 2 electrons. That means a total of 4 electrons are commonly shared by the 2 oxygen atoms. Then it forms a double bond. Nitrogen. In the formation of nitrogen molecule, each nitrogen atom contributes 3 electrons. Means total 6 electrons are shared by 2 nitrogen atoms. Here a triple bond is formed. This is ammonia molecule. One nitrogen atom forms covalent bond with 3 hydrogen atoms to form this molecule. Here all the 3 bonds are single bonds. This is methane molecule. CH4. One carbon atom forms covalent bond with 4 hydrogen atoms. Here also all the 4 bonds are single bonds. Versatile nature of carbon. Carbon is a versatile element. Due to the nature of the covalent bond, carbon is able to form millions of compounds. Let us see the 2 main factors which make the carbon a versatile element. 1. Catenation. Carbon has the unique ability to form bonds with other atoms of carbon. This gives rise to the formation of large molecules. This property is called catenation. Let's see its definition. Catenation is the self-linking of atoms of an element to create chains and rings. Due to this property, carbon forms large molecules in the form of long linear chains, branched chains, and ring chains. In addition, carbon atoms may be linked by single, double, and triple bonds. Carbon compounds with single bonds are saturated carbon compounds. Carbon compounds with double and triple bonds are called unsaturated carbon compounds. Does only carbon exhibit catenation? No. Many other elements show catenation. For example, silicon. Silicon forms chain compounds up to a length of 7 or 8 atoms. These compounds are very reactive and unstable. Whereas carbon can form compounds with a very large number of carbon atoms linked to each other. These compounds are very stable because the carbon-carbon bond is very strong. Number 2. The second factor for the versatility of carbon is its valency. A carbon atom can form bonds with 4 other carbon atoms or with other elements whose valency is 1. Carbon can bond with oxygen, hydrogen, nitrogen, sulfur, chlorine, etc. These compounds will have specific properties. The bond that carbon makes with other elements is very strong, which makes these compounds exceptionally strong. The reason for the strength of the bonds of carbon is due to its smaller atomic size. Due to the small size of the carbon atoms, the nucleus is close to the shared pair of electrons and it holds these electrons strongly. The bonds formed by elements having bigger atomic size have weak bonds. So these are the reasons for the versatile nature of carbon. Saturated and unsaturated carbon compounds. We already learned that compounds with single bonds in their structure are saturated compounds and compounds with double or triple bonds are unsaturated compounds. C2H6, ethane. Is it saturated or unsaturated? Let us draw its structure to know whether it is saturated or unsaturated. First link carbon with carbon using a single bond. Then link 3 hydrogens with 1 carbon and 3 with the other. The valencies of carbon and hydrogen are satisfied and no double bonds are formed. So this is a saturated compound. Now let us write the structure of C2H4 ethene. First link carbon with carbon using a single bond. Then link 2 hydrogens with 1 carbon and 2 hydrogens with the other with single bonds. The valencies of hydrogen are satisfied, but the valencies of carbon atoms are not satisfied. Now draw another line between the 2 carbon atoms. Now the carbon valency is satisfied. Here this compound has got a double bond, so it is an unsaturated compound. In the same way, let us draw the structure for C2H2, ethyne. Here we need to draw a triple bond between the 2 carbon atoms. So this is also an unsaturated compound. So we understood that carbon compounds with single bonds are saturated carbon compounds and carbon compounds with double or triple bonds are unsaturated carbon compounds. Unsaturated carbon compounds are more reactive than the saturated compounds. Chains, branches and rings. Butane C4H10. We can write its structure in 2 ways, like this and like this. This is the straight chain structure of butane and this is the branched chain structure of butane. Both the structures satisfies the valency of carbon and hydrogen. Both of them have the same formula. We can call these 2 compounds as structural isomers. The compounds with identical molecular formula but different structures are called structural isomers. In addition to straight chain and branched chain structures, some carbon compounds form ring structures. Such compounds are called cyclic carbon compounds. For example, cyclohexene C6H12. This is a saturated cyclic compound. Benzene C6H6. This is an unsaturated cyclic carbon compound. So, the compounds that contain only carbon and hydrogen in them are called hydrocarbons. The saturated hydrocarbons are called alkanes. The unsaturated hydrocarbons with 1 or more double bonds are called alkenes. The unsaturated hydrocarbons with one or more triple bonds are called alkynes. Carbon compounds and their functional groups. Carbon can form bonds with other elements like chlorine, bromine, oxygen, nitrogen, and sulfur and forms new compounds. New carbon compounds are formed when a hydrogen atom of the hydrocarbon chain is replaced by an element. The element that replaces the hydrogen atom is called as heteroatom. For example, here a hydrogen atom of this compound is replaced by chlorine atom. So here chlorine is the heteroatom. These heteroatoms forms the functional groups of the compounds. Sometimes heteroatoms pair up with some other atoms and form groups. For example, here oxygen is the heteroatom. It forms various functional groups like alcohol, aldehyde, ketone, carboxylic acid, etc. This is chlorethane. Here chlorine is the functional group. This is ethanol. Since OH is the functional group, it is an alcohol. This is acetaldehyde. CHO is the functional group. It is an aldehyde. This is acetone. CO is the functional group. It is a ketone. The properties of the newly formed compound will be totally dependent on the functional group of the compound. When writing the structure of functional group alone, the free valencies of the whole group is shown by a single line. Homologous series. CH3OH. This is methanol. It has one carbon in it. C2H5OH. This is ethanol. It has two carbons in it. C3H7OH. It is propanol. It has three carbons in it. C4H9OH. This is butanol. It has four carbons. These four compounds have OH as the functional group and are called as alcohols. Even though the number of carbon atoms in each of these compounds is different, they have similar chemical properties. Such series of compounds are called homologous series. The series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. Let us see the homologous series of alkanes: methane, ethane, propane, butane. The difference between each of these compounds is the difference in the number of units of CH2. This is the homologous series of alkenes: ethene, propene, butene, pentene. In alkanes, alkenes and alkynes, we can observe that there is a specific ratio of carbon and hydrogen is maintained. For example, in alkenes, CnH2n pattern is observed. If n is equal to 2, then the compound will be C2H2 into 2, that is C2H4. In any homologous series, we will observe the gradual increase in the molecular mass. If the molecular mass increases, the melting and boiling points also increases. Whereas the solubility of the compounds decreases with the increase in the molecular mass. That means the physical properties of a homologous series depends upon their molecular mass, whereas the chemical properties of a homologous series solely determined by the functional group. Nomenclature of carbon compounds. The carbon compounds are named on the basis of three things. 1. The number of carbon atoms in the main carbon chain. 2. The type of bonds present in the compound, that means single, double or triple bonds. 3. The functional group present in that compound. The name of a carbon compound is made up of two parts, a prefix and a suffix. Prefix is the first part of the name. It is dependent on the number of carbon atoms present in the carbon chain. If the compound has one carbon, the name begins with meth. If two carbons, it begins with eth. 3 carbons, it begins with prop, and 4 carbons, it begins with bute. If the hydrocarbon chain contains all single bonds, then the suffix becomes ane, that is methane, ethane, propane, butane, etc. If the hydrocarbon chain contains double bonds, then the suffix becomes ene, that is methane, ethene, propene, butene. If the hydrocarbon chain contains triple bond, then the suffix becomes ine, that is methine, ethine, propyne, butane, etc. If the carbon chain has a functional group, then the suffix changes according to the functional group. If the functional group of a 3-carbon compound is alcohol, then the suffix becomes -ol. For example, propanol. If the functional group is ketone, then it becomes propanone. If the functional group is aldehyde, then this compound becomes propanol. If the functional group is carboxylic acid, then this becomes propanoic acid. If the functional group is chlorine, then it becomes bromopropane. Most of the carbon compounds burn in presence of oxygen and produces carbon dioxide. Large amounts of heat and light are also released in this combustion reaction. Carbon plus oxygen gives rise to carbon dioxide plus heat plus light. If saturated hydrocarbons like butane, that is the cooking gas, is burnt in presence of sufficient amount of oxygen, it gives a clean blue flame with no soot. If these saturated hydrocarbons are giving an yellow flame, that means it indicates that there is a limited supply of oxygen to that combustion reaction. It leads to incomplete burning of the fuel and gives out yellow flame. If unsaturated hydrocarbons like vegetable oils are burnt, yellow color flame is produced with black color soot. In oil lamps, kerosene stoves, firewood stoves, black soot is formed, indicating the incomplete combustion of fuels. Fuels like coal and petroleum contain some amount of nitrogen and sulfur in them. Combustion of these substances releases oxides of sulfur and nitrogen into the air, which leads to air pollution. Oxidation. The alcohols, when heated with some oxidizing agents, they get oxidized and converted to carboxylic acids. For example, when ethyl alcohol is heated with alkaline KMnO4 or acidified K2Cr2O7, it produces acetic acid. Here alkaline potassium permanganate or acidified potassium dichromate adds oxygen to the alcohols and make them into acids. Hence, these substances are called oxidizing agents. The substances that are capable of adding oxygen to other substances are known as oxidizing agents. Addition reaction. Vegetable oils have long unsaturated carbon chains. Animal fats have chains of saturated fatty acid. Unsaturated fats can be converted into saturated fats with the help of addition reaction. When hydrogen is added to the unsaturated fats in presence of a catalyst like nickel, the unsaturated fats turns into saturated fats. Vanaspati ghee is manufactured by using this addition reaction. This process is called hydrogenation of vegetable oils. Catalysts are the substances that cause a reaction to occur at a different rate without the reaction itself being affected. Now, substitution reaction. Substitution reactions in carbon compounds are single displacement reactions. They occur when saturated hydrocarbons react with chlorine in presence of sunlight. Chlorine is more reactive than hydrogen atoms, so it can displace them from saturated hydrocarbons. CH4 plus Cl2 gives rise to CH3Cl plus HCl in presence of sunlight. Some important carbon compounds: ethanol and ethanoic acid. Properties of ethanol. 1. Ethanol is a liquid at room temperature. It is an active ingredient in alcoholic drinks. Consumption of these alcoholic drinks is harmful to one's health. Ethanol is a good solvent and used in the manufacture of tincture iodine, cough syrups, and many tonics. Nowadays, ethanol is added to fuel like petrol as an eco-friendly measure. Properties of ethanoic acid. Ethanoic acid belongs to the group of carboxylic acids. It is also called as acetic acid. Carboxylic acids are weaker acids when compared to mineral acids like HCl. 5 to 8% of acetic acid in water is called as vinegar. It is used as a preservative in pickles. The ethanoic acid freezes at room temperature during winter in cold climates. So it is called as glacial acetic acid. Reactions of ethanoic acid. Esterification reaction. Esters are usually formed by the reaction between an alcohol and an acid. Ethanoic acid reacts with an absolute ethanol in the presence of an acid catalyst to give an ester. Ethanoic acid plus ethanol gives rise to ester in presence of an acid. Esters are sweet smelling substances. They are used in the manufacture of perfumes and flavoring agents. The esters can be converted back to alcohol and sodium salt of carboxylic acid by treating with an alkali like sodium hydroxide. This reaction is used in the manufacture of soaps and is called as saponification reaction. Soaps are sodium or potassium salts of long chain carboxylic acids. Reaction with a base. Ethanoic acid reacts with sodium hydroxide to give a salt called sodium ethanoate. Sodium hydroxide plus acetic acid gives rise to sodium ethanoate plus water. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to a salt called sodium acetate, carbon dioxide and water. Soaps and detergents. If a shirt with dirt is simply rinsed in plain water, some dirt may go away, but it will not be completely clean because most of the dirt is oily in nature and cannot be simply washed away by plain water. Soaps and detergents are used to clean the oily dirt. The molecules of soap are sodium or potassium salts with long chain carboxylic acids. So one of the end of the soap molecule is ionic in nature. It is hydrophilic, means attracts water molecules, whereas the carbon chain is hydrophobic in nature. That means it reacts with the oil. So carbon chains hold the oily dirt, whereas the ionic end get dissolved in the water. Thus the soap molecules are arranged in specific structures called micelles. When the clothes are rinsed by applying mechanical force, these soap micelles helps in pulling out the dirt and makes the clothes clean.